All right, so our last goal is to derive some derivatives of inverse trigonometric functions. So here we have, we're tasked with finding the derivative of the inverse sine of x. And the trick here is to think of this in terms of the inverse, the derivative of an inverse function, a little formula that we used previously. So if f of x is equal to whatever this is the inverse of, sine of x, then that implies that my inverse function, f inverse of x, is equal to cosine of x. Now your book doesn't use this formula, like I said. They're going to use implicit differentiation, and that's a totally valid way to do this. I just want to provide a different way of looking at it so you have a couple of ways of thinking about it. According to our, why did I write that? Inverse sine of x. Of course, I don't know why I wrote that. What I want is the derivative, so f inverse prime of x, which according to the formula we developed is 1 over f prime of f inverse of x, okay? Now we know f inverse is inverse sine of x. And we also need f prime of x is equal to cosine of x. Maybe I think I wrote this and I was thinking f prime instead of f inverse. So we need both. That means I'm looking at cosine of inverse sine of x. So this is equal to 1 over cosine of the inverse sine of x. Okay? Now I could technically leave this in this form, but in trigonometry we teach a way of simplifying expressions like this because there's a much better way of representing this. Now, one thing to keep in mind is what the domain of the inverse sine function is. The domain of the inverse sine function is the interval from negative pi over 2 to positive pi over 2, which represents the fourth and first quadrants of the unit circle. So I'm going to take this inverse sine of x, and I'm going to do this. I'm going to think of it as the angle theta, which implies that x is equal to sine of theta, or I could also write that as x over 1. Because sine, when we first learn about the sine function, we're taught to think of it in terms of opposite over hypotenuse. We're taught to think of it as a ratio. Now what I'm going to do is draw a right triangle, labeling theta as one of the acute angles in that right triangle. Now again, we've written the sine of that angle as opposite over hypotenuse, x over 1, okay? And it's important to note that this x, again, lives somewhere between negative pi over 2 and positive pi over 2. So this x could be positive or negative, and what that's going to indicate is whether this triangle lives either in the first quadrant or in the fourth quadrant, okay? So even though I'm drawing it in the first quadrant, keep in the back of your mind that it could be down here. But now that we've done that, we want to find this third side. So I would use the Pythagorean Theorem. It's going to be the square root of 1 squared minus x squared. This is straight from the Pythagorean Theorem. Now notice that because this leg of that right triangle is to the right of the y-axis, whether the triangle itself is in the first quadrant or the fourth quadrant, notice the base is still to the right of my y-axis. That means that this thing will be positive no matter what, regardless of where I drew this right triangle. Another way of thinking of that is that the cosine of an angle is always positive if that angle is either in the first or fourth quadrant. We know that from trig. So that means I don't need to worry about a plus or a minus here. I know that it's going to be positive. Now that we've done this, if I were to take the cosine of this angle, I could think of that as adjacent over hypotenuse. square root of 1 minus x squared over 1, or just the square root of 1 minus x squared. So what that tells me is that if I wanted to take the cosine of the inverse sine of x, the inverse sine of x is what we labeled theta, so that this thing is really the cosine of the inverse sine of x. And we got this expression. So this thing simplifies down to 1 over the square root of 1 minus x squared. And that is our derivative for the inverse sine function. Notice it doesn't involve any trig or any inverse trig. It's 1 over a radical with a polynomial on the inside. Okay? So I'm going to do another one where we're going to do the derivative of the inverse tangent function, and then I'm just going to list the 6 functions that we need to know derivatives of. The inverse tangent function, it turns out when you get to calculus 2, is actually the most useful of the inverse trig functions, particularly when we're finding integrals. That's kind of what the main focus of study in Calc 2 is. So this is a really important one. The derivative I'm going to approach in the same way. So again, f of x would equal tangent of x if we want f inverse of x to be the inverse tangent function. Also, we know that the derivative of the tangent function is secant squared of x. Okay? So now I'm going to use that formula that we talked about. This implies that f inverse prime of x is equal to 1 over f prime of f inverse of x, which would be secant squared of inverse tangent of x. Okay, that's equal to 1 over secant squared of inverse tangent of x. Also, the inverse tangent function has almost the same domain as the inverse sine function. It's the first and fourth quadrants. The only difference is that it does not include the endpoints of negative pi over 2 and positive pi over 2 because the inverse tangent function is undefined there. But we're working in the same 2 quadrants, quadrants 4 and 1. Okay, I want to take the same approach as before. I'm going to say tangent inverse, or inverse tangent of x, we're going to think of as an angle theta, which implies that x is equal to tangent of theta, and again, I could also write that as x over 1. So same idea, I'm going to create a right triangle, label that angle theta, and we're going to remember that because of the restriction that we talked about here, this triangle could technically be either in the first quadrant or in the fourth quadrant down here. Tangent is opposite over adjacent, so I have x over 1 here. So the hypotenuse, according to the Pythagorean theorem, would be the square root of 1 plus x squared. Okay? So now let's look for secant of theta. This would equal the reciprocal of the cosine function. Adjacent over hypotenuse is cosine, so hypotenuse over adjacent is secant. Or in other words, root 1 plus x squared over 1, which is the same thing as the square root of 1 plus x squared. Now notice, this guy right here is not just secant of theta. Remember, tangent inverse is the same thing as theta. It's secant squared. So I need to square this result, and that's just going to give me 1 plus x squared. So that means that my derivative is equal to 1 over 1 plus x squared. Okay? I only wanted to derive 2 of them because it's time consuming to do all 6, and the approach is very, very similar for all of them, so it's better, you know, if you want to know how to find these derivatives, it's better to do that as an exercise. The idea here is essentially the same. So notice here's our derivative for inverse sine, here's our derivative for inverse tangent. The others you can derive on your own. One thing I want to point out, your book makes mention of this, the derivatives of the inverse cosecant and inverse secant functions are going to be they could potentially look slightly different depending on how you define the domain of these functions, because there are different ways of defining the domains of these depending on the textbook that you use. And the only difference is if you define the domain slightly differently, you may end up with absolute values around this x here. But we're going to be working with these versions. So to wrap things up, I want to do one example where I'm finding the derivative of the arc cosine of x squared. Okay, notice that this is a composite function, so I need the chain rule. The derivative of the outside, the derivative of arc cosine, would be the same thing as the derivative of inverse cosine. This is just alternative notation for that. And according to that, that's equal to negative 1 over the square root of 1 minus x squared. But I need my inside function to be showing up there, so it's actually x squared squared. Chain rule, right? Then I multiply this by the derivative of the inside, 2x. Putting this all together and simplifying, this is the same thing as negative 2x over the square root of 1 minus x to the 4th. Okay, just doing a little bit of simplification. And that's it. So that's going to wrap up section 3.6.